Now in this lecture we'll find out the area of the green semicircle using two different methods. In the drawing we have two semicircles. This is the white semicircle, this is the green semicircle. In addition, we know that this is 9 cm AC. This equals to 5 units in its length. This is 9 cm CB. That is equals to 1 unit in its length. Again, our mission is to find out the area of this green semicircle. So we start with the first method. And we join points P and B together by a straight line. In the next step, I'll copy the white semicircle in a new page and we'll implement rule 7 on this white semicircle. Firstly, this is the white semicircle that I copied from the original drawing. AB is the diameter of this white semicircle, so I'll write it down. Actually, by joining points P and B together by a straight line, we can do peripheral angle APB. This is peripheral angle APB that is subtended on AB, that is the diameter of this white semicircle. So here we can implement rule 7. I'll repeat quickly on rule 7. According to rule 7, if a peripheral angle subtends on the diameter of the circle, then it is equals to 90 degrees in its size. So here we have a circle, 9 cm AB is the diameter of this circle, and we have here peripheral angle ACB that is subtended on AB, that is the diameter of the circle, therefore peripheral angle ACB equals to 90 degrees in its size. So whenever you have a peripheral angle that is subtended on the diameter of the circle, it must be equal to 90 degrees in its size. So we can actually implement rule 7 in our drawing. Why? Because in our drawing we have peripheral angle APB. This is peripheral angle APB that is subtended on AB, that is the diameter of this semicircle. Therefore peripheral angle APB according to rule 7 must be equal to 90 degrees in its size. So this peripheral angle APB, it is a right angle according to rule 7. Likewise, we join points P and C together by a straight line. In the next step, I'll copy this green semicircle in a new page and we will implement rule 7 on this green semicircle. So actually, this is the green semicircle that I copied from the original drawing. Here, this side segment AEP, this is the diameter of this green semicircle, so I write it down. AEP is the diameter of this green semicircle. Actually, by joining points P and C together by a straight line, we create the peripheral angle ACP. This is peripheral angle ACP, and it is subtended on AP. This is the diameter of this green semicircle. Therefore, according to rule 7, peripheral angle ACP must be equal to 90 degrees in its size. So this peripheral angle ACP, it is a right angle. This is the original drawing. From this original drawing, it is very easy to see. This is angle A. That is a common angle. It belongs both to the green triangle APC, and this angle A also belongs to triangle APB. So angle A is a common angle that belongs to both triangles. So we define the size of this common angle A as alpha. So in this right triangle APB, this is the common angle A that is equal to alpha according to our definition. So in the right triangle APB, this angle equals to alpha. This angle equals to 90 degrees. Therefore, this third Vincent angle must be equal to 90 degrees minus alpha. Why? Because 90 degrees minus alpha plus alpha is 90 degrees, and 90 degrees plus 90 degrees, it is 180 degrees. That is the sum of the angles in any triangle. Likewise, we have here the right triangle APC. In the right triangle APC, this is angle A, that is equals to alpha according to our definition. So in the right triangle APC, this angle equals to alpha, this angle equals to 90 degrees, therefore this third missing angle must be equal to 90 degrees minus alpha. In the next step, I'll copy this green right triangle APC and this right triangle APB in a new page, and prove that those two right triangles are similar to each other according to angle similarity rule. So actually, those are the two right triangles that are copied from the original drawing. In the next step, we will prove that those two right triangles are similar to each other according to angle similarity rule. So we prove this is the right triangle APB. The right triangle APB is similar to this right green triangle APC according to angle similarity rule. So why those two right triangles are similar to each other? First of all, those two angles they are both equal to 90 degrees, therefore they are equal to each other. So actually this is angle APB in the right triangle APB. And it is equal to this angle, is actually angle ACP in the right triangle APC. So I repeat again, angle APB in the right angle equals to angle ACP in the right angle. They are both equal to 90 degrees, therefore they are equal to each other. In addition, this is angle alpha that belongs to both triangles. Here you can see that angle alpha is in the right triangle also. So angle alpha is a common angle that belongs to both triangles, so we can find out that angle alpha equals to itself is a common angle that belongs to both triangles. So if we relate to angle alpha as it is belongs to this right triangle, it will be defined as angle PAB, and it is equals to itself. So if we relate to angle alpha as it is belongs to this right triangle, it will be defined as angle PAC. Again, this equation means that angle alpha equals to itself. We just call to angle alpha two different names. Angle alpha equals to itself is a common angle that belongs to both triangles. And finally, those two angles they are both equal to 90 degrees minus alpha, therefore they are equal to each other. So actually this is angle PBA in the right triangle. And it is equal to this angle, that's actually angle APC in the right triangle. Repeat again, we actually found out that angle PBA in the right triangle equals to angle APC in the right triangle. They are both equal to 90 degrees minus alpha, therefore they are equal to each other. So we actually found out that all the triangles in this right triangle APC are correspondingly equal to all the triangles in this right triangle APB. Therefore, those two right triangles are similar to each other according to angle similarity rule. So I write it down. So the right triangle APB is similar, this is the sign of similar, to the right green triangle APC, according to angle similarity rule. And from the fact that those two right triangles are similar to each other, we derive that the following relationship exists between their sides. We derive that side AB in this right triangle over side AP in this green triangle equals to side AP in this right triangle over side AC in this green triangle. Repeat again. We derive that side AB in the right triangle over side AP in the green triangle equals to side AP in the white triangle over side AP in the green triangle. What is the length of AB? AB in total equals to 5 plus 1, that is 6. Again, AB equals to 5 plus 1, that is 6. AP is the missing side, so we leave it as it is. AC equals to 5 units in its length according to what is given as the question. Again, AB is 6 and AC is 5, so in total we shall find out that 6 over AP equals to AP over 5. We will cross multiply this equation. And we get that 5 times 6 is 30. So 30 equals to AP times AP, that is AP squared. 30 equals to AP squared. We take a root out of this equation. And finally, we get that the missing side AP equals to the square root of 30 units in its length. So actually, this is the missing side AP, and it is equals to the square root of 30 units in its length. AP is the diameter of this green semicircle. If the diameter AP equals to 2, it means that the radius of this green semicircle must be equal to the diameter over 2. That is to say, the radius R of this green semicircle equals to AP over 2. So I write it down. The radius R of the green semicircle equals to the diameter AP over 2. The diameter AP is square root of 30. So square root of 30 over 2 is the radius of this green semicircle. So the radius R equals to the square root of 30 over 2 units in its length. Our mission is to find out the area of this green semicircle. The area of this green semicircle equals to pi r square over 2. So I write it down. The area of the green semicircle equals to pi r square over 2. So the area of the green semicircle equals to pi. The radius R of this green semicircle equals to the square root of 30 over 2. And R equals to the square root of 30 over 2. Therefore, R square is square root of 30 over 2 square divided by 2. So the area of the green semicircle in total equals to pi. And remember, square root of 30 square is 30. Over 2 square is 4 over 2. So the area of the given semicircle equals in total to pi times 30 over 4 over 2 is 30 over 4 times 2. So here we have 30 over 2 is 15. So in total the value of this expression equals to 15 pi over 4. 15 over 4 is 3.75, therefore in total the value of this expression is equals to 3.75 pi, and 3.75 pi is 11.78. In conclusion, actually found out that the area of the given semicircle equals to either 3.75 pi square units, or in terms of numbers, it is equals to 11.78 square units. I repeat again, we actually found out that the area of this given semicircle, that is the area that we are looking for in this question, equals to either 3.75 pi square units, or in terms of numbers, the area of this given semicircle equals to 11.78 square units. So we finished with the first method. In the next step, I present to you how to find out the area of this given semicircle according to the second method. In the second method, we'll join points P and P together by a straight line. And I will copy the white semicircle in a new page, and we'll implement rule 7 on this white semicircle, exactly as we did in the first method. So actually, this is the white semicircle that I got from the original drawing. We know that AB is the diameter of this white semicircle, so I write it down. Actually, by joining points P and B together by a straight line, we can deduce peripheral angle APB. This is peripheral angle APB, and peripheral APB is subtended on AB, that is the diameter of this white semicircle. Therefore, peripheral APB must be equal to 90 degrees in its size according to rule 7. So this peripheral APB, it is a right angle. So here we found out that this peripheral APB is a right angle. According to rule 7. That is to say, line segment BP is perpendicular to line segment PA. Again, line segment BP is perpendicular to PA because of the fact that angle APB is a right angle. So, line segment BP is perpendicular to the diameter PA of this green semicircle. Again, line segment BP is perpendicular to the diameter PA of this green semicircle. And we know that the center of any circle or semicircle must be located somewhere on the diameter of the circle or semicircle. So the center of this green semicircle must be located between points P and A. So here, this is point O. This is located on PA, and it is the diameter of this green semicircle. So point O is the center. Again, point O is the center of this green semicircle. Point P is a point on this green semicircle itself. Therefore, PO is the radius of this green semicircle. We define the radius of this green semicircle as R. Therefore, PO equals to R. In conclusion, we shall find out that line segment BP is perpendicular to the radius PO of this green semicircle. Again, line segment BP is perpendicular to PO, that is the radius of this green semicircle, or line segment BP is perpendicular to the radius R of this green semicircle. And whenever you have a line segment that is perpendicular to the radius, you can implement rule 1. I'll repeat quickly rule 1. According to rule 1, a tangent to the circle is perpendicular to the radius 1 to its point of tendency. So in the domain we have a circle, OM is the radius R of this circle, and we have line segment AB is perpendicular to the radius MO of this circle. Again, line segment AB is perpendicular to the radius MO of this circle. And according to this rule 1, line segment AB is defined as a tangent to this circle. Actually, line segment AB is tangent to this circle as point M. Therefore, line segment AB is defined as a tangent to this circle. Again, line segment AB is defined as a tangent to this circle, and it is tangent to this circle as point M. Point M is the point of tendency of tangent AB with this circle. So we can actually implement this rule 1 in our drawing. Why is called in our drawing? We know that this is line segment BP that is perpendicular to the radius PO of this green semicircle, and whenever you have a line segment that is perpendicular to the radius, then according to rule 1, the line segment must be defined as a tangent to the circle. And because of the fact that line segment BP is perpendicular to the radius PO of this green semicircle, line segment BP is a tangent to this green semicircle. Again, because of the fact that line segment BP is perpendicular to the radius PO, that is equal to R. Therefore, line segment BP is defined as a tangent to this green semicircle. Line 7 BP is a tangent to this green semicircle, and so I write it down. If we found out that BP is a tangent to the green semicircle, in addition, if you focus on the common external point B, if you focus on this common external point B, and we draw a straight line towards this green semicircle, it will cut this semicircle at 2 points, C and A. So from the same common external point B, we have here chord CA of this green semicircle. In conclusion, we found out that from the common external point B, we have tangent BP to this green semicircle, and we also chord CA that was created by drawing a straight line from common external point B towards this green semicircle. And therefore, we can definitely implement here rule 10. I'll repeat quickly on rule 10. According to rule 10 is true in any circle. So in any circle, if AB is any chord, we have here AB, that is chord of this circle, and we have also from the same common external point P, tangent PT, that is tangent to this circle, is point T. So in this drawing, the following equation is true, that PT square equals to PA times PB. Again, PT square equals to PA times PB. So we can implement rule 10 in our drawing. Why? Because in our drawing, if we focus on this common external point B, from this common external point B, we have tangent PB, that is tangent to this circle at this point B, and from the same common external point B, we have here chord CA. So all the requirements of rule 10 are satisfied, and therefore according to rule 10, the following equation will be true, that BP square equals to BC times BA. Again, BP square equals to BC times BA. According to rule 10, if you focus on the common external point B, the following equation will be true, that BP square equals to BC times BA. Tangent BP is the missing side, so we leave it as it is. So PP square equals to BC. BC is 1 times BA. BA in total equals to 1 plus 5, that is 6. Again, BA in total equals to 1 plus 5, that is 6. So in conclusion, according to rule 10, we found out that BP square equals to 1 times 6, that is 6. BP square equals to 6. We take a root out of this equation, and finally we found out that the missing tangent BP equals to the square root of 6 units in its length. This is the missing tangent BP that is equals to the square root of 6 units in its length. In the next step, I'll copy this right triangle APB in a new page, and we'll implement the Pythagoras theorem in this right triangle APB. According to the Pythagoras theorem, in any right triangle, the square of the hypotenuse equals to the sum of the squares of the perpendiculars. The hypotenuse AB equals to 5 plus 1, that is 6. And we just right now found out that PB equals to the square root of 6 units in its length, which is actually a tangent to this green semicircle at point P. Here by PT is the evaluation for Pythagoras theorem. So actually, this is the right triangle APB that are going from the original drawing. I repeat again that the hypotenuse AB is 6, PB equals to the square root of 6 units inside, and the only missing side is side AP. According to the Pythagoras theorem, in this right triangle APB, AB square equals to AP square plus PB square. Again, AB square equals to AP square plus PB square. So I write it down. AB square, that is the square of the hypotenuse, equals to AP square plus PB square. AB is 6, therefore AB square is 6 squared, that is 36. And it is equal to AP square. AP is the missing side, so we leave it as it is. Plus PB square. PB is square root of 6, therefore PB square is square root of 6 squared, that is 6. So in total, we found out that 36 equals to AP square plus 6. Here we subtract 6 from this equation, and we get that AP square equals to 36 from 6 is 30. So AP square equals to 30. We take a root out of this equation. And finally we find out that the missing side AP equals to the square root of 30 units in its length. This is the missing side AP. Is equals to the square root of 30 units in its length. AP, it is actually the diameter of this green semicircle. Therefore, the diameter over 2 is the radius of this green semicircle. So we define the radius of this green semicircle as R. Here you can say that the radius of this green semicircle equals to R. So the radius R of the green semicircle equals to the diameter AP over 2. AP is square root of 30, therefore square root of 30 over 2 is the radius of this green semicircle. So the radius R of the green semicircle equals to the square root of 30 over 2. Our mission is to find out the area of this green semicircle. So the area of the green semicircle it is of course equals to pi r square over 2. So write it down. So the area of the green semicircle equals to pi. The radius r is square root of 30 over 2. Therefore r square is square root of 30 over 2 square divided by 2. So the area of the green semicircle in total equals to pi times square root of 30 square is 30 over 2 square is 4 divided by 2. So in total the area of the green semicircle equals to pi times 30 over 4 over 2. 30 over 4 over 2 is 30 over 4 times 2. Here we have 30 over 2 is 15, so in total the value of this expression is 15 pi over 4. Fifteen over 4 is 3.75. Therefore, the value of this expression in total is 3.75 pi, and 3.75 pi is 11.78. So, in conclusion, we found out that the area of the green semicircle, this green semicircle is equals to either 3.75 pi square units, or in terms of numbers, it is equals to 11.78 square units. Repeat again. In both methods, we actually found out that the area of this green semicircle equals to either 3.75 pi square units, or in terms of numbers, it is equals to 11.78 square units. So we finished with the second method. In the next step, I will summarize the lecture. We'll start with the first method, of course. In this lecture, we found out the area of this green semicircle using two different methods. So we start with the first method. In the drawing, we have two semicircles. In addition, we know that line segment AC equals to 5 units in its length, line segment CB equals to 1 unit in its length. Again, our mission is to find out the area of this green semicircle. So, in the first method, we join points P and B together by a straight line. And then I copied this white semicircle in a new page, and we implemented all 7 on this white semicircle. Actually, this is the white semicircle that I copied from the original drawing. AB is the diameter of this white semicircle. Here, AB is the diameter of the white semicircle. Actually, by joining points P and B together by a straight line, we created a peripheral angle APB. This is peripheral angle APB. And this peripheral angle APB is subtended on AB, that is the diameter of this white semicircle, and therefore according to rule 7, we know according to rule 7, any peripheral angle that is subtended on the diameter of the circle must be equal to 90 degrees in size. Therefore, this peripheral angle APB is a right angle according to rule 7. Yeah. In the next step, we join points P and C together by a straight line, and I copied this green semicircle in a new page, and we implemented rule 7 on this green semicircle. Actually, this is the green semicircle that I copied from the original drawing. AP is the diameter of this green semicircle, and By joining points P and C together by a straight line, we create the peripheral angle ACP. This peripheral angle ACP is subtended on AP. That is the diameter of this green semicircle. And therefore, according to rule 7, peripheral angle ACP must be equal to 90 degrees in its side. Why? Because according to rule 7, any peripheral angle that is equal to 90 degrees in its side must be equal. Any peripheral angle that is subtended on the diameter of the circle must be equal to 90 degrees in its side. Therefore, peripheral angle ACP must be equal to 90 degrees in its side. Here, it's a right angle. So this is the original drawing. It is very easy to see from this original drawing that this angle A is a common angle that belongs both to the green triangle APC, and this angle A also belongs to triangle APB. Therefore, angle A is a common angle that belongs to both triangles. So we define the size of this common angle A is alpha. So this is the common angle A. It is defined as alpha. So in the right triangle APB, this angle equals to alpha, this angle equals to 90 degrees. Therefore, this third missing angle must be equal to 90 degrees minus alpha. Why? Because 90 degrees minus alpha plus alpha is 90 degrees, and 90 degrees plus 90 degrees is equals to 180 degrees. That is the sum of the angles in any triangle. Likewise, if we focus on the green triangle APC, this is the common angle A that is equals to alpha according to our definition. This angle equals to 90 degrees according to rule 7. Therefore, this third missing angle must be equal to 90 degrees minus alpha according to the rule that the sum of the angles in any triangle is equals to 180 degrees. In the next step, I copy this green triangle APC and this white triangle APB in a new page, and we prove that those two right triangles are similar to each other according to angle similarity rule. So actually, those are the two right triangles that are coming from the original drawing. So why those two right triangles are similar to each other? First of all, those two angles are both equal to 90 degrees, therefore they are equal to each other. In addition, this is angle alpha. Angle alpha is a common angle that belongs to both triangles. You can see that angle alpha is also belongs to this green triangle. So we can write down that angle alpha equals to itself as a common angle that belongs to both triangles. And finally, those two angles are both equal to 90 degrees minus alpha, therefore they are equal to each other. So actually proved that all the three angles in this right green triangle APC are correspondingly equal to all the three angles in this right triangle APB. Therefore, those two right triangles are similar to each other according to angle similarity rule. Repeat again, and actually proved that the right triangle APB is similar. This is the sign of similar to the white green triangle APC according to angle similarity rule. And from the fact that those two right triangles are similar to each other, we derive that the following relationship exists between their sides. We derive that side AB, this right triangle, over side AP in this green triangle equals to side AP in this right triangle over side AC in this green triangle. Repeat again. We derive that side AP in the right triangle over side AP in the green triangle equals to side AP in the right triangle over side AC in the green triangle. Or AB over AP equals to AP over AC. AB, what is the length of AB? AB equals to AC plus CB. So AB in total equals to AC, that is 5, plus CB, that is 1. So in total, AB equals to 5 plus 1, that is 6. AB equals to 6 and AC equals to 5. So we substitute AB by 6 and AC by 5. So in total we should find out that 6 over AP equals to AP over 5. Here we first multiply this equation and finally found out actually that 5 times 6 is 30. 30 equals to AP times AP, that is AP squared. So 30 equals to AP squared. We took a root out of this equation and finally found out that the missing sign AP equals to the square root of 30 units in its length. So actually, this is the missing sign AP, that is equals to square root of 30 units in its length. AP is the diameter of this green semicircle. So the diameter AP is square root of 30, therefore the radius is the diameter over 2. So the radius of this green semicircle R is AP over 2. Again, the radius R of the green semicircle equals to the diameter AP over 2. The diameter AP is square root of 30. Therefore, the diameter over 2 is square root of 30 over 2. So in conclusion, we found out that the radius R of this green semicircle equals to the square root of 30 over 2. Our mission is to find out the area of this green semicircle. The area of this green semicircle equals to pi r squared over 2. Repeat again. The area of the green semicircle equals to pi r squared over 2. We just right now found out that r equals to the square root of 30 over 2. If r is equals to the square root of 30 over 2, r squared equals to the square root of 30 over 2 squared. So in total, the area of the green semicircle must be equals to pi times square root of 30 over 2 squared, that is r squared over 2. So in total, the area of the green semicircle equals to pi, square root of 30 squared is 30, over 2 squared is 4, divided by 2. So in total, the area of the green semicircle equals to pi times 30 over 4 over 2. 30 over 4 over 2 is 30 over 4 times 2. So in total, the area of the green semicircle equals to 30 pi over 4 times 2. Here, 30 over 2 is 15. So in total, the value of this expression is 15 pi over 4. 15 over 4 is 3.75. Therefore, in total, the value of this expression is 3.75 pi. 3.75 pi is 11.78. So actually, in both methods, we found out that the area of this green semicircle equals to either 3.75 pi square units, or in terms of numbers, the area of this green semicircle equals to 11.78 square units. Repeat again, that in both methods we arrived to the same result. Okay, thank you very much.